All right, so what we're doing is just finding expected value with these three scenarios. We've got box A has four $10 bills, a single 100, so that's a 0.8 probability and a 0.2 probability for each of those. Box B is 400 and 100, but it still breaks down to a 0.8 and a 0.2 probability for those. Now, box C has $28 in it in ones, and the scenarios are you can have all of box C, so they're basically saying you can have all of the $28, or you can have the expected value of A, or the expected value of B. So we need to find the expected value of either one of those. So it's going to be 0.8 times the 10. Remember, it's your expected, the outcome times the probability that it will happen. And you just add those up, so it's 0.2 times 100. And you do this, actually, it works the same way for both of these. So 0.8 times 10. And if we add this up and do the math, we're going to see that we end up with a probability, an expected value of, so that's 100. An expected value of 28 for all three of these. Now, this is not so much an expected value, it's just a guaranteed amount. So all offer the same expected winnings. The answer is E. So if you got D, chances are you just forgot to read this bit of it. So the expected value, if you could only pick one bill from box C, is going to be $1, which would make you think, oh, it's D, but that's not the case. Okay, that's your bell work for the day. Okay, and here's the outline for today. I will tell you in fifth hour, we didn't quite get through everything. We got through everything except the very end. We might go a little faster this time, we'll see. So we're going to start looking at the binomial distribution a little bit more. And I wanted to, first of all, take us back to this demonstration from yesterday. And I could put in some random numbers. So let's say we had 80 trials. Each trial had a success of 0.4 for success. And you can see this does look somewhat normal. We're going to come back to this if we get this far in class today. We'll come back to this and look at it again. But of course, what we can do here is we can calculate the probability of getting anywhere from 0 successes up to, let's go with 30. And of course, this app here online will kind of find the probability for us. And you can see this does look like a normal CDF situation where we've got kind of this area under the curve being calculated. And then of course, something we can do a little different with the binomial distribution is we could go to, let's say 34. We want to find out the probability of getting exactly 34 successes. And it'll show us that. And now you can see there's about an 8% chance of getting exactly 34. So we can do a little bit more with the binomial than we can with the normal distribution because we don't find the probability of exactly one outcome. We get just a range of outcomes with the normal. All right, so I wanted to show that, and now we're going to jump over to see how to do that on our calculator. All right. So if we do this, we can see, we're able to calculate, okay, so we talked about that. We can find, and I put area under the curve in quotes because it's not, anytime we do that, it's an approximation. And so if we're kind of thinking of it as an area under the curve. Now we can do more with binomials just like we talked about. So here are the two types of questions that can be asked that we can answer using some functions on the calculator. First of all, we can answer the question, what's the probability of getting up to X number of successes? So what's the probability of getting 30 successes, up to 30 successes? And this is what we call the binomial cumulative distribution function, binomial CDF. We could also ask the question, what's the probability of getting exactly X number of successes? And that's going to be the binomial probability distribution function, binomial PDF. Now, this should look somewhat familiar. We've already used normal CDF quite a bit. Binomial PDF we've never used the normal PDF. It doesn't make sense to calculate the exact probability of a single point in a normal model, but with a binomial, it does make sense. They're discrete values. Okay, so we're going to look at how to do that. All right, so let's—
You as well, Mr. Davis,
okay.
and everyone else.
All right, we're gonna look at an example here.
Yeah, baby.
Pedro drives the same route to work on Monday through Friday. Actually, this is the example we looked at yesterday, so we're not gonna reread it. But there's a 55% chance the light's gonna be red. 10 days we're gonna be looking at as our sample, and y equals the number of times that the light is red. Find the probability the light is red on exactly 7 days. Now we have answered this question already. It's the last thing, one of the last things we did yesterday. But now we're going to do it instead of by hand. We're going to use binomial PDF. We're looking for exactly 7 days. So that's going to be an example of using the PDF function. And it's pretty straightforward. So on your calculator, you're going to want to get into your distribution, second variables. Should have some familiarity getting to that. And you're gonna, it's easier actually to scroll up to get to your binomial distribution functions. You've got binomial PDF. And when you get to that, you've got 3 parameters to put in. You've got your trials, which is the number of trials. So here we've got 10 days that we were getting information on. The probability, P, is that there's a 55% chance that on any given day there's a red light. And the X value you want to find out on exactly 7 days, that's going to be your X value. So I'm going to put 7 right there. And when you plug this in, you should see this on your calculator screen after you paste it. You won't necessarily see the very beginning of it, depending on which calculator you have. But 10, 55%, and 7. Oh, and I skipped ahead, but you can just hit enter and get the answer. If you remember the answer from yesterday, we got the same thing. It's 0.1665, which is what we calculated by hand. Now the calculator does it in about 10 seconds. So that's the shortcut. And that's, of course, from here forward, what you'll probably be using every time, unless there's a specific problem that asks you to show your work using the formula, which I don't know that that would ever happen, but anyways. Let's see what we've got here. So now we're going to look at a slightly different example, same scenario, but now we want to find the probability that the light is red on no more than 6 days. So in this case, we're talking about a CDF function. So the cumulative distribution function. So same process to get to it. So second variables, but now it's going to be binomial CDF. And still 10 trials, still 55% probability of getting it right. And now in this case, it's going to be the number of trials up to which we're interested. So since it's no more than 6 days, you want to go from 0 to 6. And I can paste that. You can see what it should look like on your screen. And it looks like we've got a 73% chance that on any, that, let me see, what am I trying to say? That up to 6 days of the week, Pedro will run into a red light. Okay. So any questions on that? Were you guys able to go through and get all that?
For mine, I have the U and the O. What would I put in there?
Oh, U and the O?
Yeah.
Are you on a TI Inspire?
I'm on the TI 84 Plus. Am I on a different, am I on a wrong mode or something?
Maybe so. So you went to binomial CDF?
So second, as far as, oh, binomial. I was in normal.
Oh, okay. Yeah, I've done the same thing so many times when I meant to get to binomial. It's just habit to go to normal.
All right, yeah, that makes sense then.
Okay.
All right, thanks.
So there we are. Okay, so yeah, the important thing to remember is that the binomial CDF function is really the same thing as like finding the probability of getting exactly 0 red lights plus the probability of getting exactly 1 red light plus the probability of getting 2, 3, 4, 5, and 6. You just keep adding up the probability of getting that many successes, and then you just add them all up. So the slow way of doing it would be binomial PDF over and over again. So CDF, of course, just speeds that up. There are some limitations to this function, and we'll see that. And we're gonna run through an example from the book. So in this case, we've got an Olympic archer able to hit the bullseye 80% of the time. Each shot is independent of the others, which is an important assumption. Remember with Bernoulli trials, they have to be independent. And we'll assume the same probability. And of course, there's binary. It's hitting the bullseye or it's not. If she shoots 6 arrows, what's the probability of each of the following results? We're only going to look at B, D, E, and F. We're going to skip A and C for right now. We'll come back to those. So the probability that she misses the bullseye at least once. So, well, I'll just ask, what do you think we need to do for that question? So let me kind of guide thinking a little bit. When you go through 6 trials of shooting an arrow, you can make 0 bullseyes, 1, 2, 3, 4, 5, or 6. Which of these scenarios are, satisfy this condition? She misses the bullseye at least once.
Normal CDF.
We're not going to do normal.
I mean, binomial, by whatever.
You got it.
Yeah.
You got it. Binomial CDF. So of course, in the case that she gets 6 bullseyes, did she miss any?
No.
No. So she didn't miss any for 6, which means every other outcome is an outcome where she missed at least 1 bullseye. So there you go. It's that binomial CDF, and I'll just go ahead and write it down. We have 6 trials. There's a 55, or sorry, I was going back to the other example. There's an 80% chance she's going to make any one of those bullseyes. And we want the probability up to 5 successes. All right. And when I did that, I got 0.738. Which is crazy to think that there's about a 26% chance she's going to hit 6 bullseyes. Yeah, that's like a lifetime goal for me. All right. So let's look at some other things going on. These last 3, we'll just look at D and F, or D and E. All right, yeah, that's what we'll do. D and E. So the probability she gets exactly 4 bullseyes. What do we do? What function are we using for this?
Normal PDF.
Not normal.
Sorry, binomial.
Yeah, it's just a habit, and as long as you're clicking that right on the calculator, you're good. So yeah, binomial PDF, because we want an exact number of successes. So binomial PDF, still 6 trials, still 0.8, and then our input here, hopefully we can all see. I'm trying to go through this a little bit fast. So it'll be 4 as the number of successes we're looking for. And as soon as you guys have that number, you can write it down. I'll just put an equals right here and you can put what the answer is. There it is, 0.246. That's the probability of getting 4 bullseyes. All right, and the only other one I wanted to look at, so hopefully this is all good for D. So for E, she gets at least 4 bullseyes. And I want to go back to this real quick. Here are the possible outcomes of 6 trials. And which, just circle from that list of outcomes, circle the ones that satisfy this condition. There it is. Yeah, you can circle them individually, you can circle them as a group, but you got it right there. At least 4 means 4 is okay, 5 is good, 6 is good. But we want the probability of those. You could do this 2 ways. So you could get the binomial PDF of each one of these and add it up. Or what's another thing you could do?
Binomial CDF.
Binomial CDF of what? So I'll just set it up 6 trials, 0.8, but what are we going to go up to?
Three.
3. Now, I don't know if anyone has a TI Inspire and can tell me if this is different for them, but I believe everyone's TI calculators will only measure for the CDFs from the bottom up. I don't think the TI Inspire will do anything different. But anyways, you can correct me if I'm wrong on that. You should only have the option for your X value, which is going to always measure from 0 successes up to whatever you decide. So in this case, we're going to say up to 3. So if we have this combined probability, then what do we do to find the actual probability we're interested in? I don't know if I was very clear. With our calculator, we can find the probability of this. And that binomial CDF gives me the probability of getting 0, 1, 2, 3. I want the probability that she gets at least 4. So what do I do for my final step?
You subtract it from 1.
There you go. So I can really just do this. 1 minus that cumulative probability will give me the probability that she gets 4, 5, or 6. And you can do the 1 minus after the fact. You can just run the binomial CDF first. All right. And just for time's sake, I'm going to put my answer, and if you guys agree, you can react whatever way you choose. Okay, got thumbs up, nods, share the screen, camera's off. All right, good all around. All right, let's go ahead. And I'm not going to do the last one because it's just another binomial CDF. You can figure out how you would approach that. Okay. We've got now the mean and the standard deviation. So we talked a little bit about the fact that the binomial distribution looks like a normal distribution in a lot of ways. Now, the mean of it is, I think, pretty intuitive. So remember, a binomial setting is determined by having a set number of trials. So in this case, we might go through 20, in the last one, it was 6 trials. But let's say we have a different scenario. We're rolling dice 20 times. We have a 10% probability of particular success. So what we might think is if I got a 10% probability of success and I'm going to do this 20 times, well, 20 times 10% gives me about 2 successes. So it's, I think, a pretty intuitive idea. If I asked you how many times would you get heads if I asked you to flip 100 times, most of you would say, oh, about 50 times, because you're just doing 0.5 times 100 to get your 50, right? So it's a pretty intuitive logic, and that gives us this formula right here for the mean. So we just take the number of trials, and we just multiply by the probability of success for each trial. And I don't have to write this out. We already know what n means, and just make sure it's really clear. So I'll just put probability of success. Okay, really intuitive. So as great and intuitive as the mean is, the standard deviation, not so much. There is a math box in your textbook. I don't know if you guys took the time to read that to understand, but it uses the calculation of standard deviation for random variables, and it kind of goes through using binomial variables for it. And I think it's a really good explanation if you can follow the math and the logic of it. But honestly, for our purposes, it doesn't really matter where this formula comes from. Though again, I should say, I do encourage you to figure it out and understand it. Okay, so the standard deviation is going to be the square root of n times p times 1 minus p. Now your book uses q, but again, I don't ever use that, just to keep it kind of simpler, I think. And this is exactly how it's going to appear in your AP formula sheet. So if you already have that downloaded, you can go and you can find this, and you'll see that's exactly what it says. Okay. So standard deviation, now this is a good thing. It makes sense because when we have a binomial distribution that's approximately normal, which is not every case, but in some cases, then we can say right from the beginning, well, I know what the mean is going to be, and I know what the standard deviation is going to be. And I can just figure it out based on two numbers, n and p. So that's pretty nice and pretty simple. All right, so if we look at this one, we're only going to do the first 2 parts of question 20. Our archer that was shooting 6 times, and the probability of success was 0.8, just to remind you. We're going to figure out how many bullseyes we expect her to get. So remember, this is asking really for expected value, which is just the mean. And we already know that's n times p. So, I mean, we got those numbers. It's about as simple as it gets in stats. So there it is. You can write that number in. $4.8. Thank you. All right, so that's the expected value, the mean right there. The standard deviation, still not much more to it. So now it's going to be square root of n times p times 1 minus p. You do not have to have these formulas memorized. I think it's really worth saying, because there's going to be so much formula overload before too long. So it's just important to know, you don't need to know these formulas by heart. You just need to know where to find them and which test to use, which calculation to use, and look up the correct formula. All right, so in this case, we can just fill that in. Just for time, I'm going to fill this in. If you've already done the math, you can fill that in. Okay, we got an answer coming in. Perfect. There it is. And if we go to 3 decimals, that would round up to 0.980, but that's right there in the ballpark. Really good. Not more than in the ballpark, it's just right there. Okay, we're going to skip part C. I don't even know if we're going to come back to it, but that's going to be kind of a different situation going on. And we'll get to that. Is it happening right away? No, we're going to do a little bit more. I don't know how much of this one I want to do, but let's just say that same archer, same probability of 0.8, but now she's shooting 10 arrows. So how about I just do this, the mean of this and the standard deviation. And you guys can fill in those numbers real quick. All right, so these two calculations are not terribly difficult, but really the way this would look is something more like a skewed distribution right here. But we do know that the mean is about 8 and the standard deviation is 1.265. Okay, again, we'll come back to whether or not it's appropriate to use a normal distribution for this in a little bit. So that is good. This is just more practice with binomial PDF and CDF. So you guys can try that. If you have questions and you're not sure how to do this, stick around after class, we can go over it. All right. So the 10% rule, this is kind of a weird thing, but it'll make sense, I think, in a second. So a lot of times, and we went through this with earlier probability stuff, there's the probability you get with replacement versus without replacement. And frequently we're sampling without replacement. So if we were sampling students in the school, we're not going to ask the same student twice. So we're technically sampling without replacement. So that means it's not independent. There's not the same probability of being selected second as there is being selected first. Okay, if we wanted to be 100% accurate, we could use more complex calculations, more complex statistics, and there's what's called a hypergeometric distribution, like it says. We're not going to go into more detail on it, but it's got a cool name. All right, you can learn about hypergeometric distributions when you go off to college and you continue studying stats, because that's what you'll all do, right? Okay, we can compromise on this. We have a way of saying, all right, the math isn't perfect. These aren't truly independent. We are changing the probabilities when we select without replacement, but as long as we're not selecting more than 10% of the population, we're not too far off from the true measure. And that's the 10% rule. So this is kind of to summarize this, because this 10% rule, we're going to see it basically for the rest of the semester. And the rule is basically saying we're allowed to use our simpler calculations with binomial probabilities and geometric, which we'll do in a second. We're allowed to use this simpler math because the approximate is really not too far off from the true answer. And we'll show some examples with this. And I'm going to edit this a little bit just to make it go a little faster. I'm going to say we're only picking 4 coins, not 5. So we've got 100 colored coins, and you can see the colors of the coins in a bag. You pull 4 of them with replacement. What's the probability that all of them are not green? So we can see 75 out of 100 are not green. So there's a 0.75 probability. And we just do that 4 times. So I'll just raise that to the 4th power. And there's about a 0.316 probability that we're going to pull 4 coins and none of them are green. Okay, that's fair enough. Those are definitely independent. There is replacement. So let's run the same thing again, and not 5, but 4 coins. And now we're going to say that there is no replacement. When we pull a coin out, it stays out. Probability that all of them are not green. Now we have to do a little bit more complex calculations. 75 out of 100 times, now there's only 74 non-green coins out of 99, then 73 out of 98, and then 72 out of 97. So if I find that probability, and I'm just doing the probability really quick, I got 0.310. If you're doing the calculation, you can double check it. Okay, so with replacement versus without replacement, truly independent right here versus not independent, we can see there's not much difference. We're talking about 0.6% difference between those. And if we had even more, if this is 1,000 and we were running the same experiment, that difference would be even more negligible, right? So now we're going to do one more example right here. But now let's say we've only got 20 coins in the bag. And it's split still evenly between the 4 colors. And this is going to be a coin pulled without replacement. So now I go from, again, not green. So there's 15 out of these 20 tokens that are not green. But then the next time around, there's only 14 out of 19. Next time around, there's only 13 out of 18. And then the next time around, there's only 12 out of 17. All right, so we can do that math real quick. And I got 0.282 when I did that. So not independent here either. So the last two are not independent, but this one is less than 10% of the sample was pulled, and this one is more than 10% of the, of the population. So we've got some, the 10% rule is being followed right here, and it's not much difference. The 10% rule is being violated in the last one. You can see, I think about a 3.5% difference is a pretty big difference. So you can see the, mathematically, you can see why that 10% rule is there. Okay, so just to go back a slide, this is really the takeaway. We are allowing ourselves to use simpler models, simpler math, because the approximate answer that we end up with isn't going to be really that far off from the true answer. So that's what the 10% rule lets us do. Okay, and we will come back to that. So now let's look at geometric probabilities. I should add in right here, the reason we're going kind of fast through all this, hopefully getting through all of it, is tomorrow I'd like to just do a bunch of practice problems as you're getting ready for the next test. But we'll see how much of that we can do. All right, so remember with the binomial, we're basically saying, here's a set number of trials, how many successes are we going to get? And we don't care where those successes come. If it's 4 successes out of 6, we don't care if it's the last 4, the first 4, or any combination of 4 throughout. So that could be some type of problem that we have, but maybe that's not at all what we're interested in. Maybe instead we want to know, how long is it going to take us until we finally get a success? So there's something that only has a 1% chance of happening. How many times am I going to have to do that until I finally succeed? Of course, you might be able to guess the answer to that one right now. But this is related to geometric probability. Okay. And your chapter actually started off with this. So now, this came up a little earlier, but I am not a good free throw shooter, as opposed to our basketball player yesterday, who was a 72% free throw shooter. Highly respectable. Let's just say I shoot 20%. Let's be generous. And what's the probability that the first shot I make is on the 8th shot? Now, we're going to calculate this by hand really quick. So I've got this happening. I missed the first, and I missed the second, and I missed the third, 4th, 5th, 6th, 7th, and I finally make the 8th. I only have a 20% chance of making a free throw if that's my true shooting percentage. So I've got an 80% chance of missing. So I'm going to say my probability of a miss is 0.2. Or actually, I'm going to say the probability of, okay, I'm saying it's wrong. The probability of success is 0.2. And then right here, I'm going to put 1 minus p, which is the probability of failure, is 0.8. So that's where this is coming from, the 0.8, 0.8. I'm not going to write it for all of them, but there's a 0.8 right here also. And then a 0.2 when I succeed. So I can just multiply all this together. All right, so that's really, if I summarize this down, I'm not plugging into the calculator just yet. What I'm doing is I'm taking my failure probability, 0.8, and I'm doing that 7 times. I'm just going to do that to the 7th power, and then I'm multiplying by the probability of success. All right, so that can be something pretty quick to put into the calculator. And I got 0.0419. All right, now this leads us to our generic description, generic formula for geometric probability, which is this right here. So again, it's the probability of failure times all but one of the number of trials, and then finally a probability of success for the last one. And this is going to tell me the probability that my first success is on this particular event. All right, now that might seem like a bizarre question. It can be useful, or that might be, it's like a bizarre kind of probability to calculate. But there are times where, you know, that can be helpful. We'll talk about how the geometric becomes more useful with other things. But there you go, that's also in the formula sheet. So it's not something you have to have memorized. All right. Now we can do this same calculation even faster. This is the geometric PDF. So this is going to give us the probability that the first success is exactly at whatever trial, the xth trial. So we're going to put this in our calculator. I'm going to go to second, variables. Sorry, so it's a distribution. The very last ones are your geometric probability functions. So geometric PDF, E on the list, we only have 2 values to plug in. I've got a 20% chance of making it. That's 0.2, and I've got 8 is the X value that I want to see if I can make it. And of course, when I calculate that, I get the exact same number. If you plug both calculations into your calculator, you know, you can see that maybe right there, but it's the same exact number. So a little more straightforward. All right, so this is a problem we already looked at. Maybe I should pause right here. Are there questions on this so far? All right. I'm jumping around just a bit today in class. We're gonna kind of come back to this. How do we know if it's geometric versus binomial? I'm gonna jump back to that in a minute. But we're only gonna answer questions that are geometric right now. So we've got the first one. We've already seen this problem, but now we're only gonna look at A and C. Okay, so in this one, we've already done these. It says, what's the probability that her first bullseye comes on the 3rd arrow? So what do we got here? What do we need to do?
Um, 0.2 times 0.2 times 0.8.
All right, and that can be done. That would get us the answer. Just to get us trained on this a little better, I'm going to use instead binomial PDF, where I can kind of accomplish the same thing without having to think through even that much. So what is your P
Would
going to
it
be
be
for?
geometric PDF?
You're right. I apologize.
It's okay.
Okay, let's reset. We're going to use geometric PDF to make it a little easier. All right, thanks for catching that. So geometric PDF, and what is our P?
.8.
0.8. So that's going to go right there, 0.8. And X value here is going to be?
Tress.
You got it. You can see right there. Looks like, well, you guys can fill that in. Thank you very much. Okay, now the first bullseye comes on the fourth or the fifth arrow. The first thing I'm going to say about this is keep in mind these are all mutually exclusive probabilities. You can't have the first one be the first one be the second, and the first one be the third, right? It's only going to be one of those. So when we find the geometric PDF of 1, 2, 3, 4, 5, those are all mutually exclusive and we can add them. So keeping that in mind, I'm just going to put the probability of 3 or 4 right here. I'm just going to put that, and I'm going to let you guys calculate that. And I screwed up. We're looking at this one. 4th or 5th, not 3rd or 4th. I'll change that. Okay, that is the answer right there. And you can do this 2 different ways. Well, it's really kind of 2 ways we can approach this. You could just get the geometric PDF of 4 and 5. Anyways, sorry about that. You can do it for 4 and 5 and then just add them after the fact, or you could just plug it in your calculator and add them both at the same time. But whatever the case, that's really what you're doing right there. Any questions on this one? Okay. Let's look at this. What else do we have going on? Okay, so that's one thing. We could find out the probability that one particular place, the time that the first success happens, which is a very limited question and probably isn't most of the time where you're going to get the most use out of geometric probability. So maybe it's not so much, is it going to be the 8th try, but the probability that I won't make a free throw before the 8th try. What's the probability that the 8th will be the first possible time I could make it? So not the probability that's exactly on the 8th, but what's the probability that I haven't made it at all before it gets to the 8th, which is a different question. So we're really asking, what's the probability that I don't make it the first time, or the second, or the third, or the fourth, and so on, up to the 7th shot. Now that's geometric CDF, the cumulative probability. All right, so what finding the probability of the first one means the probability I'm going to make it the first time. Then I can find the probability I'll make it the second time, and so on. So we would go to the geometric CDF. It's the very last one on the list, so it's easy to get to. And our p-value is still 0.2 for this one, because I'm not a good free throw shooter or anything related to basketball. Our x value is now 7 because we're interested in everything up to, but not including the 8th try. All right, so when we do that, I'll just write this down real quick. So the 79%, what is that 79% probability saying? What is it referring to?
You have a 79% chance of not making any baskets until your 8th try.
All right, and actually and this is where it's confusing. It's actually the other way around. So it's a 79% chance that by the time I shot my 7th basket, or leading up to the point I'm about to shoot my 8th basket, there's a 79% chance I will have made one. Because what it's saying is, I've got the probability that I'll make it on the first try, the probability that I'll make it on the second, on the third, and I'm adding all those up. So at any point between the 1st and 7th, I might have made it. And there's a 79% chance it's going to fall within that 1st through 7th shot. But there is, obviously, it means the complement. 1 minus that 79% means there's a 21% chance that I'm sitting there on my 8th shot and I still haven't made one. Does that make sense?
Yeah.
Okay, so it's always, and it's just good to keep this in mind, it's always the probability of success that you're calculating. So if these are all the probabilities of success from 1 to 7, then what I want is the complement, the probability that I actually failed all those times. Okay, so we're just going to talk through that. Okay, so it just says right here, we just find the complement of it and we're good. Okay, we have a problem here? Yeah, we do. All right, we got a computer chip manufacturer. 2% of the chips fail a quality check. What's the probability that the 5th chip you test is the first bad one you find? All right, so what is this going to be? Of our newly learned functions, is this binomial PDF, binomial CDF, geometric PDF, or CDF?
Geometric CDF.
Okay. It is geometric. It's actually PDF in this case, because we're looking for the probability it's exactly the 5th.
That's what I meant. Whichever one
Okay.
was the first one.
Oh, okay. Well, yeah. Anyways, we'll get to that. So, actually, I'm not going to write anything. You can just write down the answer. What is that probability? I'll just put the equals right there and someone can write it. There it is. All right, so it is pretty close to a 2% probability still. And maybe it's worth it right here to show what a geometric distribution looks like. We already have seen the binomial one looks, eventually it can look somewhat normal. Maybe sometimes it's not that clear looking, but it does have that kind of normal distribution for the binomial. But the geometric instead looks like this. And this would either be something that looks like an inverse function or a power function, which I think is ABX. So one of those two functions, that's what it really looks like. And we'll talk about power functions more later in the semester. But keep in mind that the highest single probability you will have is on the very first try. Now that doesn't mean you're most likely to make it on the first try. What that means is that if you're trying to guess which particular try are you going to make it on, you have a much smaller chance of it being exactly the 5th, exactly that 5th try, than you do that it's exactly the first try. And that's just because of the way this is calculated. We'd have to calculate this probability times some fraction to get that probability, times some fraction to get the next one, and then the next one, and then this keeps going. So the probability that it's any particular trial goes down and down each time. But cumulatively, if we look at the cumulative probability that's going to happen, my first try, let's say, here's 100%. After the first try, I'm like right here. And then maybe it goes up a bit. So through time, by the time it gets to the 7th shot, I have about an 80% chance. So it's going to look almost like a square root function or a exponential decay function. So this is cumulative probability through time, and eventually you're going to have close to 100% probability of succeeding. All right, I think it's important to know what these distributions look like and how to interpret them. All right, I don't think I'm really erasing all of it. I'll just get some space here. So now, well, and the reason I kind of brought that up was, if you start off with a very low probability for it being the first time, here's 100%, here's 2%, right? So it's not going to drop off much. Your exponential decay, or rather your kind of power function, is going to look like that. It's going to be almost like a straight line coming across. Okay. That was a long little tangent that we went off on, but hopefully worthwhile. So now let's answer the next one. What's the probability that we find a bad one within the first 10 we examine? All right. So I'll just put an equal sign right here. I'm going to see if you guys can figure out how to find that. We'll go over it in case anyone's confused. Okay, so it's about an 18% chance. And just to debrief on this, this is still a geometric probability, but we're looking for a cumulative probability going from, we have a probability of 0.02 on any given one, but after 10 tries, so that would include that it's the first, second, third, fourth, all the way through 10th, a cumulative probability that of 18% that we're going to see a bad, faulty chip by then. Okay, questions here? All right. So we now are looking at the geometric setting. We talked about this with the binomial setting yesterday, and we learned bins. Geometric is going to be very similar. Keep in mind, and I put this, I'll just bring everything up on the screen and then we'll talk about it. So the B, the I, and the S are the same here because in both geometric and binomial probability, we're dealing with Bernoulli trials. So that isn't going to change. But in this case, we're looking for the first success. So even when it says, what's the probability that something doesn't succeed over the first 10 trials? Well, that means the 11th could be the first success. So if we're ever in a situation where we're looking for the first success, that's going to be a situation where we're using the geometric setting. So just, first of all, determine, is it Bernoulli trials? Secondly, determine, is this binomial? Is there a set number of trials, or is it just keep going until you succeed? And if it go until you succeed, then that's geometric. So we'll remember BIFs for that one. Okay, not much to that. So we will kind of look at this. We're not looking to answer questions on this. We're looking to kind of run through BIFs. So first of all, okay, 8% of males are colorblind. A researcher needs some colorblind subjects for an experiment and begins checking for potential subjects. What's the probability that she won't find anyone colorblind among the first 4 men she checks? That's the one we're going to be looking at. So pretend that's the entire prompt. Is this binary?
Yes.
It is. And what does this success look like?
Colorblind.
There you go. I'm just going to put CB for colorblind. And a failure means?
Not colorblind.
Not colorblind. So good, it's binary. Is it independent?
Yes.
Yeah, and we can say this is because basically we can consider it independent because it meets the 10% rule. Sure, we're gonna maybe bring in, I don't know how many people, let's say hundreds of males come in to potentially be part of this study, but that's still going to be less than 10% of all the males who could be part of the study. So it's close enough to be considered independent and the same probability. So I already answered that one. It's close enough to be considered the same probability. So finally, are we looking for the first success?
No.
And this one's a little bit tricky here. But what we're saying is the first success could be the fifth. So another way of saying that is, what is the probability that, well, yeah, the fifth is the earliest first possible success. Fifth is first possible success. I'm not going to write that out. Well, I will maybe. First possible success. So it's kind of a backwards way of approaching it, maybe not immediately obvious, but this actually is a situation where the geometric probability works, because we can still find the probability that, that there's failure for the first four, and then the fifth is the first success. So we can just basically get the complement that there is success among the first four using geometric CDF, and that would work. Does that make sense? Okay. And we're not actually calculating anything there. So now we're gonna look at geometric mean and standard deviation. All right, so we have enough time. I want you guys to calculate this on your own. I want you to estimate your own free throw shooting percentage. You know, if you shoot basket, if you play basketball, you might have a pretty good idea of that. And then I want you to, based on that percent, whatever you come up with, estimate how many free throws you think you need to take on average until you finally made your first one. How'd you come up with your answer? Now, this might not be the best scenario I set up because I already put a formula down at the bottom. I meant that to show up later, but shows what technology wasn't working so well for me. Okay, so I ask this. I'm actually not going to even make you guys answer out loud, but I ask this because there's kind of an intuitive approach to this, which, when I look at myself, and if I assume I'm a 20% free throw shooter, okay, 20%. It's 1 in 5. I make 1 in 5, therefore it's going to take me 5 shots on average. Sometimes I shoot, it might take me 12 shots before I make first try, first one. Sometimes it happens the very first shot I take. But on average, if I do this over and over and over again, then it's going to be about the 5th time that I shoot. So the way I get that is I just do 1 over that 0.2 probability to give me 5. So it's a very intuitive idea. Same thing right here. Like if I told you had a 1 in 100 chance of winning this particular lottery, then if you wanted to guarantee winning, you'd probably think, okay, so I probably need to buy 100 tickets, and then I have a pretty good chance of winning. Okay. So not much to that. There's the mean of a geometric distribution, and fairly intuitive for the mean, but again, not at all intuitive for the standard deviation. But I should point out, these are both equivalent expressions. So you've got square root of 1 minus p over p, or you got the square root of Q divided by P squared. Q is 1 minus P. So these are equivalent in the numerator. So of course the difference is they've already done the square root of P squared on the left, and here they leave it as the squared number. I prefer the one on the left, and that's what you're going to see on the AP test. That's what I'll probably use in class, but this is in the textbook, so you will see it this way. It's just a matter of preference which way you want it to be seen, but I like the one on the left more. So it is worth mentioning just one more time that a distribution of a geometric probability distribution looks like this. And I mentioned this just to say, currently, I don't even know what a standard deviation of this means, right? Because it's not a normal distribution or approximately normal. So a standard deviation of geometric probability is a weird thing. And anyways, that is all I have to say about that. But anyways, I can in my head as I'm talking, I can see some other possibilities for ways of interpreting this because we're talking about how many tries until your first success, not the probability of each one succeeding. So I can work my way through this maybe a little more. But anyways, let's move on. Here's the standard deviation of it. And just to clarify, we would probably see something more like this if we're talking about the number of tries until we get to a success. So for me, it would hover around 5. Every once in a while, I get it on my first shot. Every once in a while, it'd take me until my 9th shot. But there we go. See, I'm learning statistics as I go. So let's look at this. We've already answered part A and B, like 10A and B, but I wanted to now look at 12. So these computer chips, how many do you expect to test before finding a bad one? What do we need to do?
Geometric CDF.
Well, now we're talking about expect, so expected value. What's another name for the expected value?
The mean.
The mean. So we're just going to find the mean of this distribution. And how do we find that for geometric distributions?
1 over 0.02.
Okay, so there it is. And you can calculate that. What have we got?
50.
50. We're going to have to test about 50 of these. Again, this should make sense because 2% chance, that's 1/50th. So we'll probably have to test 50. All right, all good. And let me see. You know what? We might just be able to get through everything today. We'll see how far we go. So about 8% of males, we already started this one, but now we can actually kind of do some calculations. On average, how many men should the researcher expect to check to find one who is colorblind? What are we doing to get that answer?
Mean.
1 divided by 0.08.
There it is. It's the geometric mean. So there it is. And I heard 1 divided by 0.08. You can get a decimal answer for this. So don't worry if you get that. Okay, so she keeps looking for subjects. On average, she's going to have to check 12.5 men until she finds one that's colorblind. Sometimes 12, sometimes 13, and blah, blah, blah. You get it. The probability that she won't find anyone colorblind among the first 4 she checks, well, And we talked about that one already. The complement that it will be among the first 4. So 1 minus what?
Geometric CDF of 4 or whatever.
Okay, and we only need 2 numbers. We've got the probability, first of all, and the, let's see, the first success. Anyway, so we'll do 4 right there, because that means up to 4, and then we can figure that out. Okay, that's it, 0.716. Okay, okay, we'll just look at this one. We'll just answer C and move on. What's the probability the first colorblind man will be the 6th person checked? What is that calculation going to be?
Normal PDF.
Again, not normal, but I know you meant.
Binomial. Or geometric. Oh my God.
Yeah, luckily I'm trying to, well, we do have to learn another distribution later, sorry. But there's only 4 distributions that we have to worry about. So metric PDF, and what did you put in for your parameters?
0.08 and 6.
0.08 and 6. That's it. That's a probability. It's exactly the 6th person. What is that number? I didn't. Is it 0.0527? Okay, let's just move on so we can get some more knowledge in before the end of the day. And I know I'm rushing through a lot of stuff. It's basically the rest of the content. But again, the idea is tomorrow I want to just go through some practice problems that look like test questions. So ideally, you're kind of going through an entire practice test tomorrow. All right. So large counts condition is the last thing that we're going to do. And we probably won't, well, I don't know what we'll do. Let's just go until we call it quits for the day. We're going to put this all back into some context. We just learned how to find the mean and standard deviation of both geometric and binomial distributions. But let's focus on the binomial one. I'm going to go back to this one last time. Okay, so when I do this binomial distribution, I could have some number of trials. So we've been working with this right here. 6 trials with the Archer 0.8 probability, and this is what it looks like. Now, I think we can all agree it would not be appropriate to substitute a normal model for this, because this has a lot of, I mean, it doesn't look enough like a normal curve. So let's try something different. What if we had 20? Okay, that's looking better. Maybe if we had 200. Okay, now that looks very normal to me. All right, so I could trace a line over that, and I'd be close enough if I just decided to use a normal model with the mean and standard deviation and normal CDF calculations rather than the binomial calculations. So I can pick. I can do normal CDF, or I can do binomial CDF based on the data. Okay, now the question is, when is, where do we draw that line? Where do we decide, oh, this is normal enough, but, you know, maybe this one, that one's not normal enough, but, oh, this one is. All right, so that's kind of the question we're asking here with the large counts condition. So we do have an actual way of determining when it's appropriate to use the normal model. Okay, so I mean, it all comes down to having enough trials, because the probability will be set based on whatever the scenario is. So then we need to figure out, how do we have enough trials to make sure it's approximately normal? And here's the large counts. Now, in the book, they call it the success failure condition, but it's the same thing. And I should mention, there's not a correct name for this condition that AP expects. You just need to show that mathematically it works out. So, and here's what we want. We want to make sure we have at least 10 successes and at least 10 failures, which is kind of a weird way, but this is kind of a summary. So if we can ensure that, then it should be normal enough. So we can multiply n by p to find the number of successes, and then multiply n by 1 minus p to tell us the number of failures. So there it is. That's our check. And it seems kind of arbitrary, and maybe to some degrees it is, to some degree, but this is how we can determine that we have enough trials to make sure that there is an approximately normal distribution. All right, so let me see something real quick. So let's just try. I don't have an example just yet, but I can pick any numbers I want. So if my probability is 0.4, probability equals 0.4, then how many trials do we need to have in order to make this approximately normal? Well, we can figure that out, luckily. So, of course, this Q is 1 minus P, so that means N minus 0.4, sorry, I'm starting that off wrong. N times 0.4 has to be greater than or equal to 10. And then N times 0.6, which is a probability of failure, has to be greater than or equal to 10. So if I just divide both sides here by 0.4 and 0.4, then I can get that. So when my probability is 0.4, let's see, I'm going to need 25 trials for it to be approximately normal. Now I know it's going to be 25 because if I do this over here, let's see, 10 divided by 0.6 says this is N is greater than or equal to 16.66, so on. So, I mean, it's the bigger one. I need the bigger number of trials to make sure that this works. Okay, so we can do that. And then on the flip side, I could say, oh, we've got, a P of 0.01, a probability of only 1% something happening. And I've got 500 trials. Is that enough? I'm just going to multiply N times P, which gets me N times P is going to be 5. So I don't actually have enough. I'd need to do 1,000 in this case in order to have enough trials to call it approximately normal. So you can see what happens as the probability gets lower and lower or higher and higher, then you need more and more trials. So the fewest trials you'd need is if you have a probability of 0.5, and you can get away with just 20 trials. Okay, so it can range from 20 up to thousands. All right. So I don't know, here's what I'm going to do. It's 2:15. I will go through these questions tomorrow, 32 and 34 as the first part of class. But here's your homework for tonight. Some of it you might not feel comfortable doing based on not having seen some of the practice problems. But there you go. We'll call that good for today. We got through all the content. We'll just now practice with really reinforcing all the math that we learned tomorrow. Thanks for sticking around, and I'll see you then. Stick around if you still have questions.